Hello, everybody. My name is George Schieferdecker. I'm with BKSK Architects, and I'm presenting our project here today with our two other presenters, Will Russell and Nadine Hassan. We also have on our team Anthony Parker, who helped us put together the mock-up. And the additional individuals on our team to give a shout out to, at BKSK, we had Adele Bagley, David Kubik, Matthew Richardson, and Feng Yu. At Thornton Tomasetti, Stephanie Schober. And our partners for a component of our work, Onyx Solar, to provide a PV panel. Got it? You all set? Yeah. We also want to echo the thanks that were put out earlier to Omar Khan, to Mitchell Bring, and to especially to John Krause for setting up this event. We've found it a really wonderful collaboration between professionals, industry, and academics, and it has been enormously thought-provoking and inspiring to us as we've been able to participate, and we hope to be able to add to the storehouse of knowledge. We're very proud to be the opening act today. A special thanks also to Andy Prius and Andy Brayman, who shared their encyclopedic knowledge of terracotta, its process for assembly, and the glazing techniques. We've called our project The Power of Terracotta for a very specific reason. We have tried to combine terracotta with solar or building integrated solar panels. And we imagine a very standard kind of assembly, which is the basic brise soleil applied as a shading device onto many building facades. Make that out of terracotta with a special reflective glaze on it, and use it to reflect back to and onto building integrated photovoltaic panels to increase their efficiency and perhaps decrease the requirement for the number of panels to produce a certain amount of power. Oops. Okay. So a quick rendering of how that might fit on a facade so that we can all imagine this. As you can see, the panel is on the horizontal. The terracotta piece is on the horizontal, and the photovoltaic panel is on the vertical. The sun's rays reflect off of the terracotta and onto the BIPV. You saw in the earlier image our finished prototype, and you can sense the reflections of the terracotta onto the panel. It's also a concern of ours as to what this will look like from not only the street but inside the space below it. And so we've done a number of things to try to make that active and interesting as well. Just a quick note about our involvement as a firm with terracotta. We've applied this on a number of building facades in New York City. I've done a number of projects where we've used terracotta as a screening element in front of a glass curtain wall. We've used it for privacy, for shading. We're working within a tradition of terracotta that's very strong in New York City. And we are concerned as much about how it performs as well as how it appears both from the inside and from the outside. Additional projects. And one more project that's one of our favorites that takes terracotta to another level across the length of a facade and applies a kind of decorative application to it at the same time. So here we are concerned with taking terracotta, amping it up a notch, and having it work with PV. So I'm going to turn it over to Will and Nadine, who will carry us through our presentation.
Thanks. So as George said, we have a lot of experience working with terracotta, especially in New York City. Recently, we're also very interested in trying to integrate photovoltaics onto our buildings to help produce electricity. There's a local law in New York City now that is starting to require photovoltaic panels. And we thought for this workshop, why not explore combining those two passions? We contacted our friends at Onyx Solar, who we're looking at using on a few of our products, and they were generous enough to donate a couple of photovoltaic panels. And what makes Onyx special is that they're able to actually laminate the PV cells within 2 pieces of glass, and then use a coated glass on the exterior, so you don't get the typical sort of reading of the photovoltaic cells. You can pick any color you want. You can do screen printing. You can, there's a lot of possibilities. We chose, as you see in this photo, color that really helps in the blend with the palette of the terracotta. So we thought, well, we use terracotta all the time to do sun shading to help with to reduce the cooling loads on our building. But as we're shading the sun, like, what are we doing with that extra light? We thought, why don't we explore reflecting it onto a photovoltaic panel? We did some really quick research. There is a lot of research going on right now into how you can use reflected solar rays to increase efficiency. One thing that we found interesting is that PV cells really only generate electricity in a narrow bandwidth of light. So the infrared doesn't produce much electricity, and in fact, it tends to heat up the panels and make them wear out more quickly. So that's the one thing we'd like to explore further, is how to refine our glaze to help reflect more visible light and then actually absorb infrared light to also not wear out the panels, but also increase their productivity. The image you see on the lower left is actually, they're like heat fins to dissipate heat as the photovoltaic panel heats up. And so we said, okay, how do we most effectively reflect light onto our photovoltaic panel? We looked at current and historic technologies, particularly the Fresnel lens, which is just a technique to basically make a focal lens out of a series of smaller lenses that you can make in a very thin construction. It was first pioneered in lighthouse design and is now being used on large solar concentrating arrays. And then we obviously thought, well, terracotta, it's this amazing material that has such form-making possibilities. So what can we do with the terracotta to create basically these lenses that focus the light on the PV panel? Right outside of our office, looking out of our windows, we look at the New York Times building. It's a ceramic rain screen mounted on a curtain wall. So that was one of our points of inspiration. So we just started off exploring different possibilities of screening and reflecting light. Really, we just had a lot of fun coming up with different configurations, twisting them, doing them vertically, horizontally. All the while, every iteration, we would test with software analysis, Honeybee and Radiance, to determine their effectiveness. What we found out after doing numerous studies is that we really needed to kind of like zone in. One thing where we realized, obviously, you want to keep shading the interior, right? Like you want to let excess sun into the interior of the building. You want to shade it and not create glare. You also want to obviously not shade the photovoltaic panel, because that's the whole purpose, is to produce electricity from the sun. And we also just needed a specific location to really fine tune that what our target was. So we picked the Manhattan grid, specifically as if we were doing a south-facing building on the Manhattan grid, in using the sun angles based on that. And just as we talked with the team at Boston Valley, just with construction restraints and the fabrication restraints of terracotta, it seemed like going towards more of a shelf configuration would really suit us best, and it enabled easy analysis to determine like what the productivity of this shelf is reflecting onto the PV. One thing to note too is that we limited the projection off of the facade to 30 inches. It's a New York City zoning allowance for permitted obstruction beyond your property line. So trying to like make it local as much as possible. And I'll hand it over to you, Nadine.
Thank you. So exploring the different forms of the extrusion, we began to look into different forms, such as flat concave, flat but rotated, and then the twist. And in addition, we also explored the concave curve. And what we've done is compare each of the form and measure the energy output the power output, and we realized between the lowest and the highest power output varied by 20%. We've also realized that the twisted extrusions distributed light most evenly and resulted in the most output. So from there, we started to work with Andy Brayman and develop different glazes that will produce the most reflectivity onto the PV panels and explore different color bodies. So we started to think about, how reflective can a glaze get and how can we make sure that it works and coincides with the PV panels. From there, this is our current structure, and we've realized that the metallic glaze that we've produced actually becomes more liquid when we fire it. And so because of that, we had to actually design stops within our profile to control where the glaze stops, where it ends, what portion it covers as it is slumped on the twisted form. We also wanted to make sure that obviously it had to cover the top of the firm profile to reflect onto the PV panel, but we kind of wanted the glaze to also roll down around the profile just so it's slightly visible from the underside. From that, since this is, used to on a curtain panel, we've decided to design a very basic outrigger steel structure.
Okay, just going really quickly through this. We looked at a few different options. One with all the louvers angled at the PV, and then another one where they're sort of paired together. The final assembly, here's some photos of that. Came out really great. And what we were really excited is that we were able to wire these up and actually test them. So you can see here a quick study. We used a piece of foam that sort of approximated, say, the reflectivity of asphalt to cover the louvers and to test the generation of the power with or without louvers. And in this study, you'll see it was a sort of a cloudy day. The reading without the effect of the louvers was 1.7 watts. When it was uncovered, it went to 2.7. So quite a large increase in wattage produced. Then we took the foam and put it above the photovoltaic panel, so there's no like direct sun hitting the PV from above, and the reading was 1.5. So that's essentially purely reflected light off of the louvers and the ambient light around.